Let me look at another plant. This plant, you have one pole at z is equal to 0, another pole at z is equal to 0.6. Recall that in the previous example we had taken z equal to 1 as one of the pole locations, and now you have no poles at z is equal to 1. You have one at 0 and one at 0.6. Now let us have a look at this and see how we go about designing a controller for this. So in our design script, let us now change the system GP to 0.6. Then you have 1 by z square minus 0.6z and 0. So this is your GP, and let us continue to keep the feedback transfer function 1 by 1. Now let us see what happens. Now when I run our design.py, so you see that there is one pole at 0.6 and another at 0. This is the root locus. Okay. So now let me show you, if I go for this simple 1 by 1, which means proportional controller, I will have an issue. I will come out of the first iteration, and the second iteration, now I am going to choose. I will choose some damping, add some damping factor. This will be the closed loop pole location. So I will choose that. So you have at a gain at around 0.39, 0.4, let us say. So I will close that and then give the value of 0.4, and see the step response. See that the step response, though the response is good, the steady state is at 0.5, not 1, which means that there is a steady state error, quite a large steady state error, and this is not acceptable. So how do you improve the steady state error? So that is where the I portion comes. Just a P control won't work, you need to have a I. So now let us incorporate I in our GC and see what happens. So I will close this and then come out, and we will now try to incorporate a PI controller. I will clear the IPython screen, and let us see where we can change the controller structure. So you see here, this portion is where you can change the control structure. Let us go back to this block schematic, control block schematic. GC, for PI control structure, I need to have z equal to -1. There has to be a pole at z is equal to 1. So this is I portion, and then there is this gain portion k. So this will give you a I control structure, very simple PI control structure. Let us try this out and then see what we get. And now going back to the script. So let me include the PI part, the integrator part in the controller structure here as we are iterating, and see what is the effect. So let me run our design for this new plant. So this is z at 0.6 and z at 0. Z is equal to 0. So now let me include the numerator coefficient is 1. The denominator will be 1 and -1. I am including a pole, controller pole, GC pole at z is equal to 1. So now what happens? So this is the modified root loci, because I have included, this was the original pole at 0.6 and there was one at 0. Now included 1 at z is equal to 1. So because of this, you will see that the loop transfer function gain has increased, and therefore you will get a steady state response which will be having 0 error. So now I have to choose closed loop poles, and you can choose closed loop poles, you can choose any closed loop poles, and I can choose it only within the unit circle, here within the unit circle and here within the unit circle. So you can have you can look which is the boundary. So there is one boundary here, there is one boundary here, right? So if I click here, you will see that there is a gain of 0.23. This is the boundary. I should have less than 0.23 on this side, and on this side I have a gain of 0.3, 0.24. So this is anyway higher. So if I choose 0.23, it will be within the unit circle even on this root loci. So let us do that. I will close this, and then I will come out of that structure. So now this is where I would like to choose. So let us say I choose somewhere here which gives me a nice damping, or you have a damping of 0.46, and this is the gain 0.078 or 0.8. So let me choose that 0.08 and see the response. So now you see that this has a response, you have the second order response, but the steady state error is 0, which means at the steady state it goes to 1, not 0.5 as in the previous case, just a proportional, when we had given only a proportional gain. So this is the power of PI, and this is how you iterate in designing the PI controller. So coming back to this whiteboard, the controller now becomes, I will remove this, and then we had used 0.08, and this would form the entire control. So this is the designed K into GC for this particular plant, the controller design. So this you plug in into your microcontroller and try to control the plant GP. Recall that in one of our earlier discussion on PID controller, we saw that the structure of the PI, this is the structure of the PI, where you have a 0 and also a pole, and the pole is specifically located at z is equal to 1, and of course in the S domain we have a 0 and a pole is located at s is equal to 0. So when you look at the digital PI, we saw in the I control just previously that there is a pole at z is equal to 1. If we incorporate a 0 at z is equal to some value in the unit circle, then we will have the structure, GC will have the structure of a PI controller. So let us try to do that. We will attempt a PI controller for the same plant and see what happens. Let us go back to the whiteboard, and for the same plant here we will have the pole at z equal to 1, there will be an integrator pole, and we will have some 0 here and the gain k. So this will become the structure of the PI controller. So for the same plant, let us include a 0 and see the effect of that 0. Let me come back to IPython and execute the script file, and when the query comes for me to enter the numerator and denominator coefficients of the controller GC, we will do the modification. What we will do is, first I will do just the I control without putting the 0 and the numerator polynomial, and we will see the step response, and then we will include a 0 and then see how it improves. So now let me run design.py. So this we know, this is the GPH. I will close this, and then the numerator coefficient first without the 0, that is just I control. So this will introduce the pole at z is equal to 1. So here you can keep observing what is the GC, 1 by z minus 1. This is what we saw just previously, and you see that the root locus is going in this fashion. So let me choose the root locus point at around 0.5 damping. So 0.5 damping loci. So let me go out of this and go into the gain. Let me choose that 0.5 damping. So around 0.5 damping is where we had around 0.8. 0.08 is the gain at around 0.5 damping. So we will enter that value 0.08. This is what we entered last time, and then we can see the step response. So this is the step response. You see around peak overshoot of 1.2 and settling at around close to 45 or 50 times TS. So at the 50th step it settles down. So let me close this and come out of the while loop and then rerun the program. So I will rerun this program here, run our design again. Now this time I will introduce the 0 so that it becomes a PI controller. So what I will do is that in the numerator I will place a 0, 0.5 at 0.5, and then you have the pole at this point. So the placing of the 0 on the pole is something that you can do iteratively, and it will come out of practice. So you see that I placed a 0 so that there was this root loci. I wanted to attract it. So I placed a 0 here. This is the z is equal to 1 pole which is placed, z is equal to 1, and z is equal to 0.5, 0, I placed it here, which attracts this and then pulls in the root loci into the unit circle. So this is something that you can play around with. So now this is a PI structure, this GC. Let us now see the step response. Now I will choose the corresponding, this is at 0.47 damping, you see 0.47 damping, so around 0.38. So 0.38 is the gain. It was 0.08 in the earlier case, it was 0.38. So let us give this number for the K value 0.38 and see the step response. See the speed. You see that this is so much more improved for the same overshoot, the same damping ratio line 0.5 approximately. You see that the speed has improved considerably. 20 units, around 20 units, it is settling to the steady state value of the response. So this is PI controller for you. So here, if you look at this is the controller structure, z minus 0.5 by z minus 1, and the gain is 0.38. So if we go back to the whiteboard, the 0 part and the K part, we can now fill up the gap. So this is 0.38 and this is 0.5 minus 0.5. So this becomes your controller. This is now a PI controller that we have just designed using the root locus method. There is another class of systems that we need to consider. Consider this GP, consider this plant. The pole is at z is equal to 1. The problem is in the numerator, the 0. The 0 is at z is equal to 1.5, which is outside the unit circle. So this will reflect as a 0 on the right of the S-plane in a continuous domain system. So 0 can exist in the unstable region, but the pole cannot exist in the unstable region. So that is an unstable system. But you have several realizable plants, several practical systems where zeros are in the right of the S-plane in a continuous domain or outside the unit circle in the case of the discrete domain models. So how do we build the controller KGC for such system? These systems are called non-minimum phase systems. They are a bit difficult to compensate. However, let us have a look at it in the root locus and see if we are able to build a controller for that and how we go about doing this. So let us now go back to the script. So in the script, I will edit this line. I will change the numerator transfer function. This is 1 comma minus 1.5. So this is the 0 at z is equal to 1.5. And let me have just one single pole at z is equal to 1, so that to make the plant simpler, and then we will be able to understand how we can go about doing a controller for such a system. So then here when the query asks, we will give in the controller structure. Before that, I will introduce a small edit which will make your display a bit more better. So I am importing another module called OS, the OS module, and here I will include os.system clear. So this will clear the screen before execution. Then at this point, while the iteration is happening, so that you don't keep going to the bottom of the screen, and to clear up the mess, it may be good to have os.system function clear. So this will clear at every iteration, and we could have similar such here also. os.system clear, and in the end we can print out the K. So this is K value, and print out the GC transfer function sys GC. So you know what is the final designed value of the controller. So with this modification, these are just fine-tuning the display so that it becomes more comfortable for you. So now with this new plant here that we have incorporated, let us run the program. So I will now run rdesign.py. So you see here, observe this. So if you want, let me expand this figure window. So you see there is a 0 here at at 1.5, and you have a pole at 1, z is equal to 1. So the root locus is in this segment. So see that all the points in the root locus are lying outside the unit circle, which means that any point, so from k is equal to 0 to k equal to infinity here, all the points, all the closed loop poles lie in the right of the S-plane. So the system is always unstable. The closed loop system is always unstable. So in order to overcome this problem, what we need to do is we have to bring a portion of the root locus inside. We have to bring the portion of the root locus inside the unit circle. So that is the idea. So if I place a 0 somewhere here in between, it will break this root locus segment. Let's say I place a 0 here. So you will have in between the zeros a root locus segment, and then there is no root locus here. So you can't just place only a 0, so you need to place a pole. So let's say I place a pole here. So you have a root locus segment here, and then finally they have to reach the zeros here. So it will come out. So you will see a portion of the root loci coming within the unit circle. Then you can choose a closed loop pole location from that portion of the root locus segment. So that is the idea. So let us do that. I'll place a 0 here and a pole here, and you can play around with that. I will close that. Now here I will place 1, and at minus 1.4, close to that z is equal to 1.5, I am placing another 0 in the controller, and denominator I have 1, at minus 1 I am placing z is equal to minus 1. So this is our controller now, z minus 1.4 by z plus 1, and you see the root locus. I can expand that, and you can see that the root locus here, this segment is not having any loci, and you have the segment, root locus segment from this pole to this pole, and it goes out to meet the zeros. So I have this whole portion of the root locus here within the unit circle, which I can choose from as closed loop poles of the system. So let us do that. I will, and you see the clear screen effect, that it has cleared all the mess, and then you are starting in every iteration. So let me go out of that and then go into the next iteration for choosing the gain k. So let me choose the 0.5, around 0.5. So you see the gain around 0.5 is around 1.18. So you have 1.18 is the gain, damping is around 0.53. So around that region, so you can choose either here or here, all the root loci. So let's say 0.5 will come somewhere here. Yeah. So let us incorporate that gain of 1.17 or 18 and see what is the step response. I'll close this and then type in 1.18. So you see the step response. So here there are a few parts. One is the steady state part. Let me expand this. The steady state part, you see that it has reached the stable state, error 0, because you have one pole in the loop gain. In the loop gain, you have loop gain transfer function, you have one pole z is equal to 1. And then you have those transients. So at 0, you see from 0, it immediately goes down below negative and then starts pulling up and then tries to track the reference. So this is a very classic nature of systems having zeros on the right of the S-plane, or system having zeros outside the unit circle. Very classic because of the inversion in the phase, because of the phase change in the phase lag. So this is this is a way that you need to do to control, to build a compensator or a controller for a non-minimum phase system. So the whole concept idea is to bring the root locus into the unit circle. You have to attract them into the unit circle. So how can you do that? With minimum number of GC poles and zeros. So that is the whole trick. Now I will close this and I will say no, and you have, this is the gain that we have chosen and this is the GC structure. So this is what we will use as the controller. So let us go to the whiteboard and then mark it up. So the controller for this is K we gave it as 1.18 into the structure we had set it as 1 Z minus 1.4 divided by Z minus Z plus 1. So you have 1 0 at Z is equal to 1.4 and 1 pole at Z is equal to minus 1. So this becomes the control structure for a non-minimum phase system with the plant as shown here. In an earlier lecture in this series on digital controls, we had discussed modeling through bond graphs, modeling of a separately excited DC motor as one of the examples, and arrived at the governing equation, the state space equations that defines the model of this plant. We also saw that there are two dynamic equations, one on the electrical side and the other on the mechanical side, J d omega by dt, and on the electrical side, LA dIA by dt. So these two dynamic equations led to this model, the state space model. So you have the state vector comprising of the armature current IA and the mechanical speed in radians per second. So this is the A matrix and this is the B matrix. So we will use that to design a controller. We'll use this plant model definition to design a controller using the root locus method. VA is the armature voltage, which is an input. TL is a torque input, and load torque is not known, so it is considered as a disturbance input. So as far as the control input is concerned, it will come through this VA variable. Coming back to the script file or design.py, we need to incorporate the plant model definition here. sysgpd, it means we have to take that continuous domain model, state equations, define that and then convert that into discrete domain using sampling time, and then use the converted discrete domain model as sysgpd. So if we incorporate that here at this point in this root locus design script, it can look messy. It is better we incorporate it in another file and call it as a function. That would be a much more elegant way to do it. So let us see how we do it. So I will start making some modifications here. I will, for the moment, I will comment this line, and this line has to be replaced by something. So that should give me sysgpd, but it should be as a function that I call. So let me create my own module. So here let us say that let us create one module. Import my plant dot models. So I will be creating this my plant dot models module, and we will call it as
a short form MDL, model MDL. Now this module that we have imported, we can use it here. MDL is the module that we have imported, and within MDL, within this myplan.models, I have to create a function. I'll create a function DC motor, and that DC motor will have the complete state space model of the separately excited DC motor that we had discussed much earlier in an earlier class. Let us print GP, which should give us GPD, the discrete time model of the DC motor. So what I should get here is the discrete time model, which means that the continuous time state space model is also converted to discrete time and given as an output from this function. So let us see how we do this. And now we won't need this can be removed. So let us save this. We have to come back and edit this parts. Let us now see how we go about doing this module. So let me go to the right side, the terminal window. Observe that we are in this directory controls example where we place all the files. So let me create a directory, make directory my plant, the one that I have mentioned here, my plant. Make a directory with that name, this. So you see that my plant is a directory that is created. So it's an empty directory. We can go to the folder GUI folder view and see that my plant is an empty directory in that same controls examples. So within this we will have two files. One is the models file, what we have here, models file, which will contain the DC motor function, and another is a init file, which is a blank file. So what I will do, I will go here, I will open one more text file, empty, and I will just save. So let us go save in this my plant, and I will save it as underscore init underscore dot py. This is needed so that it can recognize it as a module. Just save this, and if you look at it here, you will see that there is a blank init underscore dot py, and here you will create one more file, which is the models file. So let me close this. I will open one more blank text file, and I will save that as models.py. Now save it. So you have init.py and models.py. Inside models.py, we need to type in the function. We need to type in the DC motor function. So let us do that. So let me type it in.
I have now entered the script for this models.py file, the entire script. It starts with few comment lines, and then we import some modules. There are two modules which I am importing, numpy as np and control as ctl. These two modules are needed because we will be using them in developing the model. Then we start the definition of the function, define the function, which is DC motor, and it takes two parameters, param and ts. Followed by the function definition. Here you have a set of comment lines within these triple quotes. where you can describe something on the syntax of the function, what each of the parameters mean, and what will be the return values. sysgpd is the return value. So this parameters, param is basically a list of parameters of the DC motor. Contains the armature voltage, armature resistance, LA, KT, B, J, these parameters. TS is the sampling time. This is useful especially when you import this model in an IPython IDE. You can type help that particular module name .dc motor. You will see these lines of code which will give you an idea of what it is. All these, after the function definition, all these lines should be indented with spaces so that Python knows that it belongs to this function. Now here in the model, the DC motor plant parameters, whatever you have passed here, should be assigned to the variables VCC, RA, LA, KT, B and J parameter from the list you take 0, 1, 2, 3, 4, 5 like that. Then the small signal model, the continuous small signal model has these 4 matrices: A matrix, B matrix, C matrix, D matrix. We just now saw what are the various matrices, the model of the separately excited DC machine, the same thing. Only note here that VA is combined as VCC into D, VCC into duty cycle D. VCC is the DC value and D is the duty cycle, which is the control input. TL is taken as a disturbance input. So therefore we will not be giving it as a control input, only D is the control input. So this is a single input and we have to take a single output from the C matrix, which is IA or omega, and that becomes a single input single output plant. So here the sysgpc, you can say call the control system toolbox ctl.ss state space matrix and then feed in the continuous domain matrices. A matrix, B matrix, take only all the rows of first column. C matrix, D, you also take only the first column elements, because TL is considered as only a disturbance input, not a disturbance and not as an input. Then you convert it, discretize the plant, sysgpz, again use the control toolbox, use sample underscore system, sysgpc, pass the continuous domain model, TS the sampling time, and the method zero order hold. Then the sysgpd, the discrete plant, is basically sysgpz, but you want to make it single input single output, so you use gpz, sysgpz.a, the same A matrix of gpz, B matrix of gpz. For the C matrix, take only the first all the columns of the first row, same for the D matrix, all the columns of the first row, and the same TS sampling time of gpz continues. So sysgpd is the one which is sent as the output of the function. So now if you get back to our design.py, it will now become clear when we say that we are importing this module myplan.models. Models is the file that we just now scripted as MDL, and sysgpd is mdl.dc motor. So within models you are using the DC motor function. Into that, let us pass param and TS. So what is TS? TS for this particular model is 0.02, 20 milliseconds, and then the params. So what are the params? So let me paste that which I have already written. So first a comment line for the param to know in which position what is there. You have VCC, RA, LA, KT, B and J for the DC motor, and then the actual param list. 24 volts for VCC, 2 for RA, 0.5 for LA, KT 0.1, 0.2, 0.02. So this is passed into the DC motor function. So this way you can make any complex plant and then call it into the R design and use it for designing the root locus. So let me quickly run through this. So let me call run R design.py. So you will see that the matrices, that is the discretized version of the separately excited DC motor is GPH, converted into single input single output system. Therefore it can be expressed as a transfer function. GPH, this is like this. So you are having two poles, one pole here and one pole here. There is no pole at z is equal to 1, and therefore you will see a steady state error. So let us make a PI controller. Let me give a structure. I will give it something like that. I have tried it out, and you can, after a few iterations, you will get it. You can also try it. I am putting a 0 at z is equal to 0.9 and pole at z is equal to 1 in order to give the integrator action. So this is the structure of a PI controller. So let us run that. You see the root locus of GPH. You can zoom this in, so you will see that I have placed this pole here, GC pole, and another 0 here. So this keeps all the root loci inside the unit circle. And let us go out of this while loop and go into the select K mode. So let me select K at this point. So you have 0.13 as the gain and a damping ratio of so much. So let us give 0.13 and see the step response. So this is the step response, which you have the 0 steady state error because we have put the PID. We have put this PI controller, which will give you a 0 steady state error. So this is how you go about designing. I will come out of this loop, designing the controller. So the controller for this separately excited DC motor plant would be K is equal to 0.13 and GC is Z minus 0.9, Z minus 1. Of course, this is not the unique solution. There are several solutions, infinite number of solutions, depends upon what you choose for the structure of GC and then what you choose for selecting K. Finally, when you are doing this root locus design, keep in mind that you are trying to make the steady state error 0, you are trying to improve the speed of response and trying to maintain the peak overshoots and its damping within certain limits. So these are the performance specification to which you are trying to design. And you need to, as a first step in iteration, iterate by choosing a proper structure for GC, and then after that you iterate by choosing a proper value of K on the root locus such that you get a proper value of closed loop poles for the system. So this is how you would do root locus design.